We've spent this series building the harness around the model: context, memory, tools, verification, orchestration, and control. I'm Merdad, and today we're asking how much of that surrounding machinery is permanent. Agentic RL trains models across long trajectories, so behaviors we scaffold outside today can move into the weights tomorrow. That doesn't make harness engineering pointless, but it changes what deserves durable investment. The harness is not only something we build around a model, it also sketches the capabilities that training may absorb next. Look at each component in your current harness and ask one question. Why does this code need to exist? Retry wrappers compensate when the model gives up early, while routing logic compensates when it chooses the wrong tool. Scratch pads preserve a thread the model might otherwise lose, and stop conditions prevent a loop it cannot reliably end itself. These are sensible production controls, not engineering mistakes. But much of this machinery compensates for limitations in today's model, and those limitations can change. Once training teaches the behavior directly, yesterday's necessary workaround can become tomorrow's redundant complexity. The central claim is that a harness is relative to both the model and the moment. The same scaffold can rescue one model, constrain another, and add needless latency around a third. As models improve, some external procedures become native capabilities, so the surrounding layer should shrink or change with them. This means a harness is not a permanent specification that you design once and preserve forever. It's a time-bound interface between current model behavior and current production requirements. Build it carefully, but keep the seams visible enough that temporary scaffolding can be removed. To understand how behavior moves inward, separate RLHF from Agentic RL. In the familiar RLHF setup, the model receives one prompt, produces one answer, and preference feedback scores that answer. In decision terms, this resembles a one-step problem, even when the response itself contains substantial reasoning. Agentic RL instead trains a sequence of actions across a long, changing episode. The model calls tools, receives observations, updates its plan, recovers from errors, and eventually decides when to stop. That is a genuine sequential decision problem, often partially observed because the model only sees returned observations. This shift changes what a tool means during training. In a prompt, the tool appears as a schema describing available arguments and expected outputs. In Agentic RL, the tool becomes part of the environment that executes actions and changes the state. The model acts as the policy, choosing whether to reason, search, edit, or call another capability. The environment runs that action, then returns an observation and some reward signal. Search R1 demonstrates this pattern by training the interleaving of reasoning and multi-turn search. Instead of scripting every search decision, training uses the consequences of those decisions to improve the policy. The useful dividing line is capability inside and control outside. Training can absorb behaviors such as multi-turn tool routing, interleaved search, error recovery, retry strategy, and knowing when to stop. Those capabilities benefit from experience across many trajectories and can become more efficient when the model performs them natively. Governance, permissions, audit trails, and organization-specific data boundaries should remain explicit in the harness. Fresh tools also stay outside because the model could not train on interfaces that did not yet exist. Inspectable controls remain external by design, not because training is behind. You shouldn't bury access policy inside frozen weights that operators cannot quickly inspect or change. Agentic RL is promising, but 3 open problems make it much harder than scoring a single answer. First is reward design. A final outcome may arrive after hundreds of actions, while many valuable intermediate steps remain invisible. Verifiable rewards work well when a unit test, exact answer, or deterministic rule can check success, but many real tasks lack that oracle. Second is credit assignment. Even with a reward, we must identify which earlier decisions actually earned it. Third is infrastructure, because long rollouts against stateful tools are slow, expensive, and difficult to reproduce safely. This frontier is therefore a systems challenge as much as an algorithmic one. A 2026 harness reflects the models, interfaces, and failure modes available in 2026. The bitter lesson suggests that hand-engineered structure covering today's limitations often gets absorbed by broader methods and more training. The practical response is not to stop building harnesses, because production systems need reliability now. Instead, design temporary scaffolding so it can leave as cleanly as it entered. Invest deeply in the substrate that survives model changes. representative tasks, realistic environments, evaluation sets, and trustworthy training data. Those assets let you test what the new model absorbed and rebuild only what remains necessary. This creates a useful connection between harness engineering and model training. Every behavior you scaffold, observe, and evaluate reveals a capability that future training can target. Your traces show where the model hesitated, which recovery worked when routing failed, and what a successful trajectory looked like. With careful evaluation and privacy controls, those traces can become training signals rather than disposable operational exhaust. Today's harness is therefore tomorrow's training data, and today's failure taxonomy becomes tomorrow's curriculum. We scaffold the current gap, measure it, train against it, then move outward to the next unresolved behavior. Carry 3 ideas into the finale. First, the harness is model relative and time-bound, so behaviors scaffolded today may become native capabilities tomorrow. Second, Agentic RL treats tools in the changing world as an environment, training complete trajectories rather than scoring one answer. Third, capability can migrate inward, but governance and inspectable controls should remain outside. The durable investment is your substrate: tasks, environments, evaluations, and data that reveal what each new model can actually handle. Build the scaffold you need today, but preserve the evidence that helps replace it tomorrow. If this series is useful, subscribe to Multi-Agent Academy, and you can also connect with me on LinkedIn. Next is video 21, the finale, the harness as a platform. We'll see how glue code around one agent becomes a shared control plane for operating many agents. Build what lasts, and I'll see you there.